evening and welcome to Tinkering with Edkelar. It is time for another Tektronix device, I think. This one is a bit more modern than the Curve Tracer and quite a bit more specialized. What is it? It's a TDR, that is a time domain reflectometer. What does it do? At the electrical level, it sends out a pulse and then measures any input on the same port. This way, it can detect and measure a reflected signal both in amplitude and duration. This is a useful way to get information about the condition of a transmission line. If the line is open or shorted, the reflected signal will show that, and the delay between pulse and reflection allows for a rather precise localization of the potential fault. Another improvised use case is to find out how much wire is left on a spool. Just look at how far away the open end is. The unit looks a bit unconventional because it was made for mobile and predominantly outdoor use, which means it has a battery pack and is almost entirely watertight. So let's see what makes it tick. First, removing all the non-factory stickers. I'm not doing paid promotions here, much less unpaid ones. Overall, the device is a bit dirty, with specks of green and orange paint for some odd reason. There is an expansion slot on the right half of the front panel. My unit came with the optional printer. This allows for direct printing of the measurement results. I'm trying to remove the front panel next, but that didn't work out as expected. For some reason the front panel isn't held in place by the shell, but rather by the chassis inside. To remove the lot, one has to undo the screws on the rear and slide out the complete assembly. Again, there's a lot of shielding going on. Since the whole idea is to measure tiny amounts of very fast signals, it is understandable that any stray input would cause a wrong result. The power switch is interesting. It's a pull-push style one. The lid has a little plunger inside, so closing the lid will push the switch into the off position. Very thoughtful, I must say. Also somewhat novel, there's a can of granules in here. Seems to be one of those moisture collecting ones. Taking apart the main components is rather simple. Just follow the screws. There are several main components, all connected with ribbon cables. The main PCB is the center of all the digital magic. CPU, RAM and ROM as well as a buffer battery are here. The buffer battery even has the nominal 3 volts. The actual measurement is done by the analog board in a dedicated can. Here, even the ribbon cable has a dedicated shielding layer. The front panel has a sandwich of PCBs. The LCD display alone has 2 for the driver chips, and there is a controller PCB on top of that that holds all the switches and dials as well as the driver for the backlight. The buttons have a rubber gasket. This thing truly is almost watertight. Not that I want to try that, but it sure would have no problem with a rainy day outside. The LCD is the weak spot of the device. It is known to fail, and the pictures on the auction had some broken pixels to prove the point. Let's see if a good clean helps. Oh, the I/O controller has a botch. Recapping. Now I think the pixel errors are caused by the flatflex connectors between the two driver boards. Somebody decided it was good to have screws on the inside of the sandwich and also solder some wires across on the other side. So every time I want to test this, I have to solder, test, resolder, curse and repeat. It took quite some time to finally have all the pixels show up again. The display is a 265 by 128 overall, with two banks of 64 pixels on top of each other. So there is 64 line drivers and 512 column drivers. Now the LCD display is quite a piece of art. It is backlit and tech decided that it might need a heating element for outdoor use, so there's a heating pad inside too. I clean all the contacts for the zebra strips and put the column PCB in again. Took 2 tries for this to hit the sweet spot with the columns. The first attempt had the upper half shifted by 1 column. The row driver board is next. It has a zebra strip to provide the column input and a flat flex for the row output. Both needed to line up perfectly, and as you can see here, the row contacts were tarnished quite badly. This one took 4 attempts until I had all the pixels line up again. The battery pack was, naturally, beyond a simple charging fix. It is made from 9 C-cell NiCad batteries. Putting in new batteries. The one I got this time didn't come with tabs on them, so I had to weld on my own. Well, no time like this time to try out the cheap spot welder then, I guess. Reassembling the battery pack. It's a tight fit. The original batteries didn't have the little knobs on the positive terminal, so they were slightly smaller. Oh, and the unit came with a line filter block, one of those potential magic smoke bombs. I replaced it with a newer one just as a precaution. Remounting the power supply. The lid is a hermetic seal and contains a little space for adapter cables and similar trinkets. The lid also comes apart into several pieces, much easier to clean that way. now, after all the bits and pieces are connected again, trial time! The first try did work, but did not look good at all. Clearly, some pixels were missing, but what's weirder is that the cursor line almost always showed up perfectly, despite the rest of the display seemingly being broken. I mean, it's the same driver lines. How is that even possible? Now to the printer. It uses a 50mm thermal roll. These are rather rare apparently, so I stocked up from a seller in Germany. Also, taking it apart for a good clean, of course. There is a stepper motor that drives the paper feed roll and drags the paper across the thermal printhead. Very simple, with only one moving part, unless you count the motor or belt. And again, a bit weird. Everything is plugged into the printer PCB except the print button on the front panel. Oh well. The pinch roller for the feed is pushed against the printhead with a spring, and the entire feeding unit can be lifted to facilitate reloading of the paper roll. Somehow this was stuck on my unit and didn't move. Oh, and yes, the pinch roller is a rubber type material, which is degraded by now. You know that tar-like stuff you find on old tape drives when the rubber belts degrade? Same stuff, only in bulk. That won't work. Cleaning up the printhead, since the roller has left quite an impression. Taking measurements for the pinch roller. I found some rubber stock online, and now I'm trying that for the first time. Let's see how that works out. First, I get the stock to length and make it nice and even. Then I drill a hole through the center. The axle has centering holes, so I use my tailstock to push it into the new roller. Okay, slightly oversized still, but now I can mount it and go over the entire length at once. Oh, and also get it to final dimensions lengthwise. And much later, since I didn't dare to take off too much at a time, I got it. A new pinch roller. To get exact results, you need to set the dielectric value of the cable. Either you have a datasheet that specifies that, or, like I'm doing here, you have a known length of sample wire and adjust it until it matches the measured length. I use a spool of wire for testing. Note that this device supports several coaxial types of cable as well as a twisted pair, which works, apparently, for regular dual-core stuff too. Nice! And that's it! Another device saved from the dumpster and a useful addition to my tools. I hope you enjoyed this project. See you next time! The pinch roller for the feed is pushed against the print head with a sprint and a... Sprint? Oh, spring!